This talk is part of a series on the Zermelo Fraenkel axioms for set theory and will be about the axiom of choice. So the axiom of choice is by far the most controversial of the axioms of set theory. In fact, there is more than one book that has been written about it. For instance, there's this book by Thomas Jeck, and there's this book by Gregory Moore, and there are also several other books that I don't have yet. So what does this axiom say? Well, it says given a set of non-empty sets, say A1, A2 and so on, we can find a set containing exactly one element from each set A something or other. So another way of stating this would just be to say the product of non-empty sets is non-empty. And some people think the axiom of choice is obviously true because if you've got non-empty sets, you can just pick an element from A1, then pick an element from A2, and just carry on picking an element from each set. And other mathematicians consider the axiom of choice to be obviously false because you haven't specified any rule for picking these elements from all the sets. So you haven't actually defined a set, you've just vaguely asserted its existence. If you look at all the other axioms of set theory, things like the axiom of the power set or the axiom of an ordered pair, they at least try to write down an explicit definition of the particular set. For instance, the power set you construct by taking all subsets of the set, whatever that means, and forming that into a set. The axiom of choice, it doesn't give you a construction of this choice function, it just asserts its existence, which is why it has been so controversial. So the axiom of choice was originally introduced by Zermelo in order to prove his theorem that every set can be well ordered. In fact, this wasn't the first use of the axiom of choice. It turns out people had been implicitly using the axiom of choice before Zermelo came along and made it an explicit axiom. And in fact, Zermelo wrote down the original Zermelo's axioms for set theory in order to be able to explain his proof that every set can be well ordered. What he was doing is he was writing out exactly what assumptions about sets he was using. So we can ask what applications of the axiom of choice are there? Well, I just mentioned the first one. It had proved an old conjecture that every set can be well ordered. There's another folklore theorem it's not a folklore theorem, there's a folklore story about this theorem, which is due to Tarski, which says that if you've got an infinite set, then it has the same cardinality as the product of the set with itself or as the sum of the set with itself. What Tarski actually did was he submitted a paper that said, this theorem is equivalent to the axiom of choice. And the story goes that the journal sent it out to two referees, Lebesgue and Fraenkel, and Lebesgue rejected it on grounds that, both assertions that Tarski made, the axiom of choice and this condition here, were both obviously false, and it was of no interest to prove that two obviously false assertions were equivalent. The other referee, Fraenkel, said that both assertions were obviously true, and it was of no interest to have an equivalence between two obviously true relations. So, as you see, it was a very controversial axiom. People had very strong feelings about whether it was obviously true or obviously false. So there are various other applications of the axiom of choice. Some well-known ones are things like Zorn's lemma, which implies all sorts of useful things like every vector space has a base, it sort of becomes quite tedious doing algebra without something like Zorn's lemma. So the axiom of choice is certainly very convenient. It makes a lot of results simpler to state. Unfortunately, it also has some rather weird consequences. So in particular, it shows things like that there is a non-measurable set. And it also shows things like the Banach-Tarski paradox, which is this famous paradox that you can take two balls of the same size and cut them up into a finite number of pieces and reassemble them into making one ball of the same size, which sounds nonsensical at first sight. I guess another rather doubtful result is that the reals can be well ordered. And again, nobody has ever managed to write down an explicit well ordering of the reals. Well, that's actually not quite true, as I'll explain a little bit later. So the axiom of choice seems to imply the existence of various objects that no one can write down explicitly. So there are some good choices of the axiom of choice and so there's some good uses of the axiom of choice and some uses that make people a little bit nervous. Well, if you don't like these applications, there are some weaker variations of the axiom of choice, which are things like the axiom of countable choice, which says that if you've got a countable number of sets, you can pick one from each. And this seems a bit safer than the full axiom of choice, because you can sort of, you can go through the sets one by one. You can do set 1, then set 2, then set 3, and so on. This seems more plausible than having to make an uncountable number of choices. There's also a slightly more powerful version of this called the axiom of dependent choice, where each set you're choosing depends on the previous choices you've made. And the axiom of dependent choice is actually strong enough to prove most of the applications of choice you need in analysis, but it's not strong enough to prove most of the rather bizarre consequences of the axiom of choice. So people of a nervous disposition might want to stick to the axiom of dependent choice. Now we can ask, what is its relation to the other axioms? So is it independent of them or whatever? And this is now fairly well understood. The first, one of the most famous early results about set theory is Gödel's result that the consistency of Zermelo Fraenkel set theory without the axiom of choice implies the consistency of Zermelo Fraenkel set theory with choice. What this means is that adding the axiom of choice is not going to give you a contradiction unless there was a contradiction already. And after Gödel's theorem, people were much happier about using the axiom of choice, because although it's not clear whether it's true or even if that's a meaningful question, it's at least not going to cause severe inconsistency problems. So I'll give a very quick sketch of how Gödel did this. So what he did was, you start by looking at the von Neumann hierarchy and so on. So the union of all these is the universe of all sets, where each v alpha plus 1 is equal to the power set of v alpha, so the collection of all subsets. And at limiting ordinals, you just take the union of everything you thought of before. And what Gödel did is he replaced it by the constructible hierarchy. Oops, so it should be L2, L omega plus 1, where L alpha plus 1 is equal to all the constructible, sorry, all the definable subsets of L alpha. So instead of taking all subsets of L alpha, you just take the definable ones. Well, the problem is I haven't explained what definable means, and actually defining definability turns out to be quite a tricky problem. So what it means is a subset that can be defined by a formula from the language of first order logic, depending on various parameters, where these are allowed to be sets you've already constructed at earlier stages, and this formula allows quantification over L of alpha, but not over the whole universe. So actually explaining exactly what this is takes a fair amount of slightly tricky work, which I won't worry about. Anyway, the point is that Gödel has now made everything so precise that you can actually well order the whole of L. So we can define a well ordering of the whole of L. And when I say define, we can write down an explicit form in the language of set theory defining a well ordering. And the reason is that each L alpha plus 1 you can define a well ordering on using the fact that you can order all possible formulas, and you have a well ordering on all these parameters. And so by sort of carefully keeping track of everything, you can well order each stage L alpha, and then you can do this in such a uniform way. You can actually define a well ordering of the whole of L. And if you've got a well ordering of the entire universe, then the axiom of choice is obviously true, because for any set, any non-empty set, you can just pick the smallest element of it in that well ordering. Incidentally, this implies we can define an explicit well ordering of the reals in at least in the constructible universe, because you can define an explicit well ordering of any set whatsoever. So, and similarly, you can define things like explicit non-measurable subsets of the reals and so on. So if anybody claims you can't actually define an explicit non-measurable subset, it depends what universe you're working in. And if you're willing to work in the constructible universe, then you can actually define these. I think I forgot to say that Gödel also proved that L satisfies all the axioms of Zermelo Fraenkel set theory if V satisfies all the axioms except for the axiom of choice. This left open the question about whether you can find models without the axiom of choice. And this turns out to be quite a bit trickier. The first result of this was proved by Fraenkel, who found a model of Zermelo Fraenkel without the axiom of choice, except it wasn't quite a model of Zermelo Fraenkel set theory. It was a model of Zermelo Fraenkel set theory with atoms. So it does not satisfy extensionality, because there are lots of different atoms that are all different but all have the same elements, because they don't have any elements at all. It does satisfy a modified version of the axiom of extensionality, where you say everything is either a set or an atom, and the sets do satisfy extensionality. But anyway, roughly speaking, the idea is you take a set of atoms, U1, U0, U1, U2, and so on, and you can now find a model of Zermelo Fraenkel set theory with atoms by just starting with A and building up. So we would start with A, and then we would take the power set of A and the power set of the power set of A, and you might call that A0, A1, and then we would take the union of all these four finite states and call it A omega, and then take A omega plus 1, and you keep going like this. So you can build up a model, a sort of universe, by repeatedly taking power sets and unions like the von Neumann hierarchy, except you're starting with a set of atoms, so you've got a set of atoms. Well, the problem is this does satisfy choice, at least if you're working inside a model with choice. So what Fraenkel then did was he take a submodel of this, and he found a rather clever way of finding a submodel that didn't satisfy choice. So what you notice is the symmetric group on an infinite number of elements acts on A, the set of atoms, and we can take all sets, well, I guess maybe let's say take all objects fixed by a large subgroup of S infinity. And what do you mean by large subgroup? Well, a subgroup fixing a finite number of points. And you can check that if you do this, then you still get a model satisfying all the axioms of ZFA, apart from possibly the axiom of choice. And now you notice that the axiom of choice isn't actually satisfied, because there is no total ordering of the set A in this model, because if you've got any total ordering of A, let's try saying U0 less than U1 is less than U2, for example, you notice that this ordering is not fixed by a large subgroup. In fact, it's not fixed by anything other than the trivial subgroup. So Fraenkel managed to construct a model without choice, provided you allow atoms. You can actually do variations of this. So Fraenkel used atoms and got a model without choice of Zermelo Fraenkel set theory, except without the axiom of extensionality. A variation of this done by Specker, Mendelssohn and Schoenfeld, instead of using atoms, they use non-well-founded sets. So what you can do is you can take a set A that contains just the element A and a set B that contains just the element B, and so on. And instead of using atoms, you can use these funny non-well-founded sets. So this gives a model of Zermelo Fraenkel set theory that doesn't satisfy choice, but it doesn't satisfy foundation either. And finally, Cohen, instead of using atoms or non-well-founded sets, used forcing to add a countable number of Cohen reals. And again, you can use Cohen reals in much the same way that Fraenkel used atoms, and this actually now gives a model of the whole of Zermelo Fraenkel set theory where the axiom of choice is actually false for much the same reason as before. So this settled the question of what the relation of the axiom of choice to the other axioms is. It's actually independent of them, that if you've got a model of Zermelo Fraenkel set theory, then you can construct from it a model where choice is true using Gödel's theorem, and a model where it's false using Cohen's theorem. In fact, the axiom of choice doesn't really add any power to Zermelo Fraenkel set theory in some sense. If you use Zermelo Fraenkel set theory to prove some statement in piano arithmetic, for example, using choice, then you can also prove that statement without choice. So some of the axioms like power set and replacement really do make Zermelo Fraenkel set theory essentially more powerful in that you can prove more statements about the integers, and some of them like foundation and choice don't really make it any more powerful. They don't increase the number of statements in piano arithmetic you can prove. So finally, I'll just give a sort of what's almost a recreational modification of choice. We can look at the axiom of choice for n element subsets. What this means is if you've got a lot of n element subsets for some fixed integer n, can you pick an element for each of them? And people have done quite a lot of work on which axioms Cm imply other axioms Cn. For instance, it's easy to see that if you can pick an element from any 4 element set, then you can easily pick an element from each 2 element set. It's slightly surprising that the converse is almost also true. If we can pick an element from each 2 element set, then we can pick an element from each 4 element set in a canonical way. And I'll sort of explain how to do this. So suppose you've got a 4 element set. Now, this has a lot of 2 element subsets, and for each 2 element subset, I can pick one of the 2 elements. And that's like saying I have on each line between 2 elements, I can choose a direction like this. So given a 4 element subset, I can choose an ordering on the complete graph. And now we can actually canonically pick one of these 4 elements as follows. So if there is a sink, pick it. By a sink, I mean something with everything mapping to it. Otherwise, if there is a source, pick it. So a source means, of course, something where all the arrows are going from it. And if there isn't a sink or a source, you can say otherwise, there are 2 points with 2 incoming arrows and 1 outgoing arrows, and 2 points with 2 outgoing arrows and 1 incoming arrow. And now what we do is we take the 2 points with incoming arrows and pick one of these, which we can do by the axiom of choice on 2-element sets. And by using a variation of Fraenkel or Cohn's result, you can show that C2 does not imply C3. And as I said, people have taken this question of which CMs imply which other CNs much further.